Hey guys, I'm going to try to finish up the water lecture here really quick so you can answer your questions a little better. I'm going to start with specific heat, which means the same thing as heat of vaporization and high heat capacity. And what this means about water is that it takes a long time for it to heat up and slow down, okay? And the reason it takes water longer to heat up is because of the cohesion, the hydrogen bonding. So if I had, let's say, a pot of oil on the stove, and I had a pot of water on the stove, let's label it up here, okay? And I put heat under it, okay? So let's say that's a flame, okay? What happens when something actually heats up is that the molecules, when you add heat energy, the molecules absorb that heat energy, and that turns into kinetic energy of molecules moving around, and that's what makes it hot. Okay, so when you put your hand, let's say you had hot water and cold water, and you put your hand in each, in the hot water, the molecules are vibrating around really fast. That's what makes it feel hot. In the cold water, they're not. They have less kinetic energy or movement. So just to understand what temperature means, it's kinetic energy of the molecules. And so if we look at oil, and oil is non-polar molecules, okay, without charges. So there's going to be no hydrogen bonding or anything between them. As soon as I add heat or a flame to this, these molecules are going to absorb the heat, start moving around with kinetic energy, and this is going to get hot really fast, okay? So oil is something we'd say would have a low heat capacity. Water, when I add the flame, remember, because I'm trying to draw like dotted lines, remember, because you have all the hydrogen bonding between the water molecules, right? Because water is polar, it forms the hydrogen bonds, or it has cohesion. So when I first add the flame, it has to first break those hydrogen bonds. And then once that's broken, all the water molecules start vibrating around and will heat up. So water takes longer to heat up than oil. Water has a high heat capacity, oil has a lower heat capacity. Okay, so why is that? That's good for living things, because we're trying to keep our temperature constant. We call that homeostasis, when you try to keep something constant. Or, we have ways to kind of heat up and cool down. We don't want our temperature spiking up and down. Also, from a larger standpoint, from like an Earth atmosphere or a ecosystem kind of level, our atmosphere is water, clouds, and water vapor. And so that makes sure that our environment around us, the temperature is not fluctuating too much. Okay. Evaporative cooling is just what it says. It's talking about the fact that when water evaporates, okay, and evaporate is when you're going from a liquid to a gas, right? So when anything goes from a liquid to a gaseous state, it's vaporizing or evaporating. When water does that, for example, with like sweating, okay, if this is your skin, when you sweat, you have water in your sweat, which is a liquid, and when that evaporates off as a gas, takes heat with it. Okay, so when something goes from the liquid state to the gaseous state, it takes heat with it. And so it basically takes heat off your skin. It's a way that we use to cool down. Also, the last one's water is uniquely less dense as a solid, okay? Ice is less dense. Ice is solid water. It'll float, okay? Now, this is different. Let's look at the phases. I know you've all had this. For most things, you have your three states of matter: gas, liquid, solid, right? And the molecules get closer together as you go from a gas to a liquid, then to a solid. For water, it's actually different. You see, your molecules are spread out in a gas. They get a little closer together in the liquid state. But when they go to get closer together to form a solid, because of the hydrogen bonding, all the water molecules kind of hydrogen bond in this pattern, and they then sort of push each other apart. And so because of the hydrogen bonding pattern, the cohesion, the solid then ends up being less dense than the liquid. And that's unique to water because of the hydrogen bonding pattern. And why is that important to living things? So it's really important in aquatic ecosystems. So if this is like a lake, when ice freezes, it floats to the top. Like if you think about like a frozen lake, it never freezes all the way through the bottom, and it doesn't freeze from the bottom up. The ice is always on the top. So let's say you have, water. Let's say this, is the cold water in here. And the molecules are getting closer and closer together as they get cold. But once they get close enough where they can start forming all these hydrogen bonds in a pattern, it then forms this, which is the solid state, which is less dense. And so this is going to float. And then the ice on the top insulates the water below it. So the water below it never all freezes. Okay, it's isolated from the cold air up here. It may be cold water, but it doesn't freeze. And this is good for aquatic life because if ice didn't float, you'd have like the ocean or a lake just freeze all the way through, and life underneath wouldn't be able to exist. Yep, so that's it for water. That was all I did and finished today. See ya.